318 times the mass of Earth. It generates auroras more powerful than all of human civilization combined, and at 13 times its current mass, it would have ignited as a star, taking every planet in the inner solar system with it. Subscribe if you want more of the cosmos. White space. Let's take this slowly. In the arithmetic of the universe, planets are rounding errors. They account for a fraction of the mass in any given star system, dwarfed by the star they orbit, invisible against the scale of the galaxy. A typical spiral galaxy contains several 100 billion stars, around most of them planets orbit. The total number of planets in the observable universe almost certainly exceeds the number of stars, and it may exceed it by orders of magnitude. Yet, for most of human history, we knew of exactly 8 of them, the 8 that circle our own sun, and we could only speculate whether any others existed. That changed in 1992, when the first confirmed planet outside our solar system was detected orbiting a pulsar in the constellation Virgo. 3 years later, the first planet around a sun-like star was confirmed. And by now, thousands of exoplanets are known across hundreds of systems. What those discoveries have shown is not what most scientists expected. The cosmos is not populated with orderly copies of our solar system. It is populated with systems strange enough to challenge every assumption planetary scientists had built over decades of studying the 8 worlds around our own star. Among those 8 worlds, the class of objects known as gas giants occupies a special place. They are not the most numerous planets. They are not the most hospitable to life. They are not even the most interesting to the majority of the public, who tend to direct their imagination toward rocky worlds with the possibility of oceans and atmospheres. But gas giants are, in a very real sense, the most consequential planets in any system they inhabit. They are the gravitational heavyweights that determine the architecture of everything around them. Understanding how they form, what they are made of, and how they behave is inseparable from understanding how planetary systems, including ours, arrive at their final configurations. No other category of body in the universe combines the fluid dynamics of a global atmosphere, the exotic material states of a deep interior, the magnetic field geometry of an active dynamo, and the gravitational influence of a small star into a single sustained object. Gas giants are where thermodynamics, quantum mechanics, magnetohydrodynamics, and celestial mechanics all converge. They are complicated in exactly the ways that make them scientifically irreplaceable. For most of the 20th century, the formation of planetary systems was treated as a largely deterministic problem. A protoplanetary disk of gas and dust collapses around a new star, and over a few million years, that disk organizes itself into planets. Given similar starting conditions, similar stellar mass, similar disk composition, the outcome would be broadly similar. Rocky planets close to the star, gas giants farther out, a rough ordering by density and volatile content. Our solar system was the template. That model did not survive the first decade of exoplanet observations intact. The first exoplanet discovered around a sun-like star, 51 Pegasi b, announced in 1995, was a gas giant roughly half the mass of Jupiter orbiting its star at a distance of less than 8 million kilometers, completing a full orbit in just over 4 days. The temperature at its cloud tops exceeds 1,000 degrees Celsius. Nothing in the standard formation model predicted this. A planet of Jupiter's mass could not have formed that close to a star. The temperature would have prevented solid material from accumulating in sufficient quantities. The planet must have formed farther out and migrated inward, driven by interactions with the gas disk. The discovery of 51 Pegasi b didn't just add a new planet to the catalogue, it restructured the entire theoretical framework for how planetary systems evolve. Since then, the catalogue of known exoplanet architectures has grown to include systems that seem to violate nearly every intuition built from studying our own solar system. There are systems where multiple gas giants orbit interior to where Mercury sits in our system. There are systems where a gas giant has been ejected from its original orbit and now travels through interstellar space, bound to no star, heated only by its own residual internal energy. There are systems with gas giants on orbits so elliptical that they pass close enough to their star to melt rock on one side of their orbit and then swing out to distances beyond Saturn on the other. Each of these configurations tells a different story about how the process of planetary formation can go. Two mechanisms have been proposed to explain the formation of gas giants. The first is gravitational instability, in which a cold, dense region of the protoplanetary disk fragments directly under its own gravity, collapsing into a planet mass object over a brief period, perhaps as short as 1,000 years. This mechanism is most plausible for very massive disks or very distant orbits, where the local density is high and the stabilizing influence of thermal pressure is reduced. It may explain some of the gas giants found at large separations from their stars, where core accretion would operate too slowly to beat disk dispersal. The second mechanism, core accretion, is the one most planetary scientists consider the dominant pathway for forming gas giants like Jupiter and Saturn. It begins not with gas, but with dust-solid particles in the protoplanetary disk, initially micron scale, that collide and stick together through electromagnetic forces and surface adhesion. These small aggregates grow into pebbles, then into boulders, then into planetesimals kilometers in diameter. The growth process at intermediate scales is actually poorly understood and remains an active area of research. There is a well-documented obstacle known as the meter-size barrier, where objects of roughly that scale tend to fragment on collision rather than growing, and where radial drift toward the stars at its fastest. How planetesimals cross this barrier is still debated. One promising mechanism is the streaming instability, in which the aerodynamic interaction between dust particles and gas spontaneously concentrates solids into dense filaments that then collapse, gravitationally jumping the meter-size barrier by forming kilometer-scale bodies almost directly. Once planetesimals are in place, growth accelerates through a process called oligarchic accretion. Larger bodies gravitationally focus material toward themselves, collecting smaller planetesimals at a rate that increases with mass. The largest bodies, planetary embryos, begin to dominate their gravitational feeding zones, sweeping up the planetesimals within their reach and clearing broad swaths of the disk. At this stage, collisions between embryos are common, and the system is dynamically chaotic, with orbital crossings, resonances, and ejections all operating simultaneously. The critical threshold for gas giant formation is reached when a solid core accumulates approximately 10 Earth masses. Below this threshold, the planet's gravity can hold only a thin gaseous envelope in hydrostatic equilibrium. The gas presses inward, and the thermal energy of infalling material presses outward, and the two balance at a modest atmospheric mass. Above 10 Earth masses, this balance breaks down. The gravitational pull of the core becomes strong enough to drive runaway gas accretion, drawing in gas from the surrounding disk at an exponentially increasing rate. A core that takes millions of years to reach 10 Earth masses can accumulate the remaining 300 Earth masses of gas in as little as 100,000 years. The transition from solid embryo to gas giant, once it begins, is swift. Where along the disk this process unfolds depends critically on a boundary called the frost line, sometimes called the snow line or ice line. At a certain distance from a young star, the ambient temperature in the disk drops below the sublimation point of water ice. Inside this boundary, water exists only as vapor. Outside it, water freezes onto dust grains, adding solid material to the local reservoir and dramatically increasing the surface density of solids. For our solar system, this boundary lies at roughly 2.7 astronomical units from the Sun, just outside the asteroid belt. The difference in solid material density on either side of this line is estimated to be a factor of 4 or more. It is no coincidence that the 4 inner planets are rocky and relatively small, while the 4 outer planets are either gas giants or ice giants. Even so, the details of Jupiter's formation remain genuinely uncertain. Current models suggest it formed in the outer solar system and then migrated inward to its current position at 5.2 astronomical units through interactions with the gas disk. This migration would have had cascading effects on the rest of the system, scattering planetesimals inward and outward, helping to populate the asteroid belt with material from beyond the frost line and influencing the delivery of water and organic material to the inner solar system. The timing of Jupiter's formation may have determined whether Earth's orbit remained stable enough for the planet to develop a temperate climate. In this sense, Jupiter did not simply form alongside Earth. It helped create the conditions under which Earth became what it is. Of the 4 gas and ice giants in our solar system, Jupiter is the one that defines the category. Its mass is 318 times that of Earth, 2.5 times the combined mass of all the other planets. If you added another Jupiter to the solar system, the Sun's gravitational center would shift by an amount comparable to the Sun's own radius. Jupiter is close to the upper limit of what a planet can be before the distinction between planet and brown dwarf becomes meaningful. Brown dwarfs, objects too massive to be planets, but too small to sustain hydrogen fusion, begin at roughly 13 Jupiter masses. Jupiter is large, but it is measurably not a star. Its rotation period of 9 hours and 56 minutes is the fastest of any planet in the solar system. This rapid spin gives Jupiter a pronounced equatorial bulge. Its equatorial diameter exceeds its polar diameter by more than 9,000 kilometers. The same rotation drives the horizontal bending visible in any telescopic image of the planet. Those bands are the visible tops of atmospheric jet streams running in alternating directions at different latitudes. Between the jets, huge cyclonic and anticyclonic systems develop, some of which persist for years or decades. The most famous of these, the Great Red Spot, has been observed continuously for more than 350 years. It is an anticyclonic storm system larger than the diameter of Earth, maintained by the shear between adjacent jet streams, powered partly by solar heating and partly by heat escaping from the interior. Recent observations by the Juno spacecraft have shown that the roots of this storm extend hundreds of kilometers below the visible cloud tops. The visible surface of Jupiter, such as it is, since the planet has no solid surface, is composed of overlapping cloud layers at different altitudes and temperatures. The topmost layer, which reflects the most sunlight and accounts for the pale zones visible in Jupiter's bending, consists primarily of frozen ammonia crystals. The warmer, darker belts represent regions where this uppermost cloud deck is thinner, allowing deeper, warmer layers to become visible. Below the ammonia cloud layer lies a deck of ammonium hydrosulfide, and below that, in regions where temperatures rise above 0 Celsius, water clouds form in much the way they do on Earth. These 3 layers together span a pressure range of roughly 10 atmospheres and a depth of only a few tenths of kilometers, a remarkably thin slice of the planet's total thickness. Jupiter's auroras, generated by charged particles spiraling along magnetic field lines and striking the upper atmosphere, are the most powerful in the solar system. They radiate continuously at radio, ultraviolet and X-ray wavelengths. The energy input from Jupiter's auroral processes alone exceeds the total power output of all human civilization. They are driven partly by the solar wind and partly by material erupted from Io. Jupiter's innermost large moon and the most volcanically active body in the solar system. Io's volcanoes inject roughly 1,000 kilograms of sulfur dioxide and other material into the Jovian magnetosphere every second. This material becomes ionized, forming a dense plasma torus around Jupiter's equator that interacts with the magnetic field to generate the aurora. Io itself is a consequence of tidal forces. Caught between the gravitational tugs of Jupiter, Europa, and Ganymede, the three moons that share a 1:2:4 orbital resonance known as the Laplace resonance, Io's orbit is slightly elliptical, and the tidal forces generated by this ellipticity flex and heat Io's interior continuously. The result is a surface covered in active lava fields, sulfur plains, and volcanic calderas that dwarf anything on Earth. The volcanoes on Io erupt at temperatures up to 1600 degrees Celsius, higher than any eruption on Earth in the modern era. Io loses material to Jupiter's magnetosphere faster than it can rebuild its crust from volcanic output, making it one of the most geologically dynamic objects in the solar system. Europa, the second large moon, presents a radically different environment. Its surface is covered in water ice, smooth enough to suggest that liquid water lies beneath. The ice is marked by systems of ridges and bands that resemble the pressure ridges seen in Earth's sea ice when tectonic forces act on it from below. Spectroscopic measurements have detected magnesium sulfate and other salts on the surface, consistent with a salty liquid ocean in contact with a rocky seafloor. Tidal heating, the same mechanism that powers Io's volcanoes, keeps Europa's subsurface ocean from freezing. The total volume of water in Europa's ocean is estimated to exceed the total volume of all the oceans on Earth by a factor of 2 or 3. Europa is one of the most scientifically compelling targets in the solar system, and NASA's Europa Clipper mission, launched in 2024, is currently en route to study it in detail. What lies beneath Jupiter's own atmosphere is a structure unlike anything found on the terrestrial planets. Imagine a probe built to survive the pressures and temperatures of the deep interior, armored not against impact but against compression and heat, powered by a reactor that could maintain instrumentation against a thermal environment that exceeds the surface of the Sun. As this probe descends through the cloud layers, the atmospheric dynamics of the upper troposphere give way to a more monotonous but more extreme environment. The wind speed begins to equalize with depth rather than following the surface jet streams. Temperature and pressure rise steadily. At a depth of a few hundred kilometers, with pressures reaching tens of atmospheres, the probe passes through cloud layers of ammonium hydrosulfide and water before entering a relatively clear zone, where the gas, though still technically a gas, is dense enough to blur the boundaries of ordinary classification. At pressures in the range of hundreds of thousands of atmospheres and temperatures exceeding 10,000 degrees Celsius, molecular hydrogen begins to transition toward its metallic state. This transition is not sharp. Unlike water transitioning from liquid to solid at a well-defined freezing point, hydrogen moves toward metallic behavior gradually over a broad pressure range. In the metallic state, hydrogen's electrons are no longer bound to individual protons. They move freely through the medium, giving it the electrical conductivity of a liquid metal. This metallic hydrogen is the material that generates Jupiter's magnetic field. The convective motion of this conducting fluid, coupled with Jupiter's rapid rotation, sustains a dynamo process similar in principle to what generates Earth's magnetic field in its liquid iron outer core, but on a vastly larger scale. Jupiter's magnetic field at the cloud tops is roughly 20,000 times stronger than Earth's at the surface. Helium behaves differently from hydrogen under these conditions. At a certain depth in Jupiter's interior, helium becomes immiscible in metallic hydrogen. The two materials, like oil and water, prefer to separate. Helium forms droplets that rain downward through the metallic hydrogen envelope, releasing gravitational energy as heat. as they sink toward regions where they redissolve. This helium rain is believed to be one of the mechanisms maintaining Jupiter's excess heat output, the energy it radiates beyond what it receives from the Sun. Saturn, which is older and more evolved in this process, likely experiences more extensive helium rain, explaining why Saturn's atmospheric helium abundance is measurably lower than Jupiter's. What lies at the center of Jupiter is one of the most actively debated questions in planetary science. The classical model assumed a discrete rock and metal core of perhaps 10 to 15 Earth masses, the original solid nucleus around which gas was accreted. Data from the Juno spacecraft, particularly its gravitational measurements, have complicated this picture significantly. The data suggest that Jupiter's core may be much larger than predicted, perhaps 40 to 60 Earth masses, but also that it is diffuse or fuzzy, meaning that heavy elements are distributed throughout a substantial fraction of the planet's radius rather than concentrated in a compact central region. This may be the result of a giant impact early in Jupiter's history, which partially dissolved the original compact core and mixed heavy elements through the surrounding envelope. If so, Jupiter's interior retains a record of a violent early phase of planetary evolution, encoded in the distribution of elements at depths no instrument can directly probe. Neptune occupies the opposite end of the outer solar system, 30 times farther from the Sun than Earth. It was the first planet whose existence was mathematically predicted before it was observed. In the 1840s, astronomers studying Uranus noted that its orbital path deviated slightly but consistently from predictions. Something was pulling it, working independently. The French mathematician Urbain Le Verrier and the British mathematician John Couch Adams both calculated where that something must be. Le Verrier's prediction arrived at the Berlin Observatory in September 1846. That same night, Johann Galle and Heinrich d'Arrest pointed their telescope at the predicted location and identified Neptune within the first hour of searching, less than 1 degree from where Le Verrier said it would be. It was one of the most precise predictions in the history of science, demonstrating that Newtonian mechanics could be used not just to describe known objects, but to discover unknown ones. Galileo had actually observed Neptune in 1612, recording it in his notebooks as a dim star near Jupiter. On at least one occasion, he noted that its position had shifted slightly relative to the surrounding stars. Had he followed up systematically, he might have identified it as a planet 200 years before Le Verrier. He did not. The discovery credit by scientific convention goes to those who recognized it. Neptune is classified as an ice giant, grouped with Uranus in a subcategory of the outer solar system that is compositionally distinct from the hydrogen-dominated gas giants. The term is somewhat misleading. At the pressures and temperatures found inside Neptune, the water, ammonia, and methane that constitute the bulk of its mass are not solid. They exist in a hot, dense, ionically conducting fluid state, a superheated high-pressure phase that bears no resemblance to anything ordinarily called ice. This fluid, sometimes described as a superionic state or a warm, dense matter, conducts electricity and may even exhibit unusual behavior, where oxygen atoms lock into crystalline arrangements, while hydrogen ions flow freely through them, effectively a solid that conducts electricity like a liquid. Neptune's interior is not cold. At its center, temperatures may exceed 5,000 degrees Celsius. Neptune's magnetic field is generated within this conducting mantle, and it has a geometry unlike that of Jupiter or Earth. It is offset from the center of the planet by roughly 13,000 kilometers, more than half of Neptune's radius, and tilted by 47 degrees relative to the rotational axis. This means that at some latitudes the magnetic field at the surface reverses direction as the planet rotates. For any hypothetical inhabitants, the magnetic North Pole would trace a large loop across the sky with each rotation rather than remaining fixed. The same unusual geometry characterizes Uranus, and both planets may generate their magnetic fields in a similar way, through convection in a relatively thin, electrically conducting layer of their mantles, rather than through deep-seated dynamo activity. Triton, Neptune's largest moon, is one of the most dynamically anomalous objects in the solar system. It orbits Neptune in the direction opposite to the planet's rotation, a retrograde orbit that could only arise if Triton was captured from elsewhere rather than forming in place around Neptune. The leading hypothesis is that Triton was originally a large Kuiper belt object, a body similar in character to Pluto, that was gravitationally captured by Neptune in the early history of the solar system. The capture process would have been dramatic, likely involving a close encounter during which Triton shed orbital energy to another object and fell into a bound but highly elliptical orbit around Neptune. Tidal forces then circularized the orbit over millions of years, converting Triton's orbital energy into internal heat. The original moon system that Neptune possessed before Triton's capture was almost certainly disrupted by the encounter, scattered into irregular orbits or ejected entirely. Today, Neptune's other known moons are a collection of irregularly shaped, dark objects in orbits that bear the marks of this early violence. Triton itself is geologically active despite its remote location and frigid surface temperature of -235 degrees Celsius. Voyager 2 detected geyser-like plumes erupting from the surface, driven not by internal heat but by solar heating of a thin nitrogen ice layer. Sunlight penetrates the transparent nitrogen ice and warms a darker substrate beneath, causing nitrogen gas to erupt through the ice in columns that rise several kilometers before being carried downwind as dark streaks. Triton is slowly spiraling inward toward Neptune. In approximately 3.6 billion years, it will cross Neptune's Roche limit, the distance within which tidal forces exceed the self-gravity holding a body together, and it will be torn apart, creating a ring system more massive than Saturn's current rings. The atmosphere of Neptune is the most energetically active in the outer solar system, despite receiving less than 0.5% of the solar energy that reaches Earth. Wind speeds in the upper atmosphere have been measured at more than 2,000 kilometers per hour, faster than any winds measured on any other planet, and faster than the speed of sound in Earth's atmosphere. The mechanism driving these winds is not yet fully understood. Solar energy alone is insufficient to account for them. Internal heat plays a role, but the precise coupling between the deep interior and the visible atmosphere is one of the major unresolved questions in ice giant science. What is clear is that Neptune's atmosphere is far from the quiet, featureless environment one might expect of a planet at the outer edge of the solar system. The blue color of Neptune has become one of its identifying characteristics. The atmosphere contains methane, which absorbs red wavelengths and transmits blue and green, giving both Uranus and Neptune similar bluish hues in reflected sunlight, but Neptune's blue is visibly deeper and more saturated than that of Uranus, despite the two planets having similar methane concentrations. Spectroscopic analysis has confirmed that some additional compound in Neptune's upper atmosphere enhances the absorption of longer wavelengths. What that compound is has not been conclusively determined. It may be a photochemical product, a complex organic molecule produced by ultraviolet radiation breaking down atmospheric methane. But this is inference rather than direct detection. Neptune is more intensely blue than physics currently predicts for reasons we do not yet understand. Saturn is the planet that most reliably stops a conversation when it appears in a photograph. Nothing in the solar system looks quite like it. The pale amber sphere surrounded by concentric rings of ice set against the black of space. Even knowing what it is, even knowing the rings are made of water ice and are in places only a few meters thick, the visual impact doesn't diminish. Saturn is one of those objects that reminds you that the universe is capable of producing things that seem designed purely for aesthetic effect. The rings span a total radial distance of roughly 300,000 kilometers, though most of that width is occupied by empty space. The main ring system, designated A, B, and C, is confined to a much narrower band, and even within that band, the distribution of material is uneven. The Cassini division, a gap roughly 4,000 kilometers wide between the A and B rings, is largely cleared of material by the gravitational resonance of Mimas, the innermost of Saturn's large moons. The density waves, bending waves, and spiral structures within the rings were revealed in extraordinary detail by the Cassini spacecraft's final series of passes between the rings and the planet. Images that show the ring structures as fine as a few hundred meters in scale. The rings are not the static, uniform structures they appear through an Earth-based telescope. They are dynamically active, sculpted by the gravity of embedded moonlets, swept by electromagnetic forces, and slowly evolving on timescales of tens of millions of years. The rings are young by solar system standards. Their composition is remarkably pure, more than 90% water ice, which, if they were ancient, would not be the case. Micrometeorite bombardment and the slow incorporation of dark contaminants should have darkened the rings significantly over billions of years. Current estimates place the ring's age at no more than a few 100 million years, possibly as recent as 100 million years, meaning they formed long after dinosaurs appeared on Earth. What created them is not known with certainty. A captured comet or asteroid shredded by tidal forces is one hypothesis. The disruption of a pre-existing icy moon is another. Whatever the original source, the material has since been processed and redistributed by the gravitational influence of Saturn's moons into the intricate structure we observe today. Saturn's atmosphere is structurally similar to Jupiter's, but noticeably calmer at the visible level. The most dramatic permanent feature is the hexagonal jet stream surrounding the North Pole, a standing wave pattern that has maintained its shape for at least 40 years of observation. The hexagon measures approximately 25,000 kilometers across, large enough to contain two Earths side by side, and extends hundreds of kilometers into the atmosphere. Its origin lies in the interaction between the polar vortex and surrounding zonal winds of different velocities. In laboratory experiments with rotating tanks of fluid, hexagonal and other polygonal patterns arise naturally from similar differential rotation, suggesting the hexagon requires no exotic explanation, only the right combination of wind speeds and latitudes. What is remarkable is not that hexagonal patterns can form, but that this one has persisted with almost no detectable change in shape or position for decades. Saturn emits approximately twice as much energy as it receives from the Sun, even more than Jupiter in relative terms. Some of this excess energy is residual heat from gravitational contraction, but Saturn's internal heat output is too large to be explained by contraction alone, given the planet's age and mass. The deficit is believed to be made up by helium rain, which is substantially more advanced in Saturn than in Jupiter. Saturn's atmosphere is measurably depleted in helium relative to Jupiter and to the solar composition, consistent with helium having rained out into the deep interior over billions of years, releasing gravitational energy as heat. Among Saturn's 80-plus known moons, Titan commands the most scientific attention. It is larger than the planet Mercury, and unlike almost every other moon in the solar system, it has a substantial atmosphere. A thick nitrogen haze that extends hundreds of kilometers above the surface and supports a surface pressure 1.5 times that of Earth's. The orange color of Titan's haze comes from complex organic molecule stolins, produced by ultraviolet radiation reacting with methane and nitrogen in the upper atmosphere. These molecules rain down onto the surface and accumulate in a layer of orange organic sediment that covers much of the terrain. Most remarkably, Titan has a methane cycle analogous to Earth's water cycle. Methane evaporates from the surface, condenses into clouds, falls as rain, flows in rivers, and collects in lakes and seas. The Cassini radar instrument mapped hundreds of methane lakes near the North Pole, the largest of which, Kraken Mare, covers an area comparable to the Caspian Sea. The rivers carving channels through Titan's water-ice bedrock are not made of liquid water. The surface temperature of minus 179 degrees Celsius is far too cold for that. But they function in exactly the way rivers function on Earth, eroding terrain and depositing sediment at their mouths in delta formations. Titan is the only world in the solar system besides Earth known to have stable liquid on its surface. The liquid is methane. The surface is ice. The rain is organic haze. It is Earth rewritten in different chemistry, operating at temperatures that would freeze nitrogen solid on any mountain in our world. Enceladus, by contrast, is a small moon 500 kilometers in diameter, small enough to fit comfortably within the boundaries of France. It should be cold, dark, and geologically dead. Instead, it is one of the most actively studied objects in planetary science. Its south polar region is marked by 4 parallel fractures, informally called tiger stripes, from which water vapor and ice particles erupt in continuous plumes that rise hundreds of kilometers above the surface. The Cassini spacecraft flew through these plumes directly, collecting samples and detecting not only water vapor and ice, but also molecular hydrogen, carbon dioxide, methane, and a variety of organic molecules, including complex carbon-bearing compounds. This chemical profile is consistent with hydrothermal activity, water in contact with hot rock on the seafloor of Enceladus's subsurface ocean, reacting to produce hydrogen through a process called serpentinization. On Earth, hydrothermal vents on the seafloor support communities of organisms that derive energy not from sunlight, but from the chemical energy in hydrogen and sulfur compounds. These ecosystems operate in complete darkness, powered by the chemistry of rock reacting with hot water. If a similar chemistry is operating on Enceladus, the question of whether the subsurface ocean hosts living organisms is not speculative fantasy. It is a question with a scientific basis. Enceladus is not in the conventional habitable zone. It receives negligible solar energy, but life as we know it does not require solar energy. It requires liquid water, chemical energy, and organic molecules. Enceladus has all three. The Cassini mission, which arrived at Saturn in July 2004, transformed our understanding of the Saturnian system more than any other mission in the history of planetary exploration. Over 13 years in orbit, it performed more than 290 targeted flybys of Saturn's moons, mapped the ring system at resolutions orders of magnitude beyond anything achievable from Earth, measured the composition of the rings, the atmosphere, the magnetosphere, and the plumes of Enceladus, and delivered the Huygens probe to the surface of Titan, the most distant landing ever achieved on another world at the time. The scientific return from Cassini changed not just the details of Saturnian science, but the entire set of questions planetary scientists knew to ask about outer solar system bodies. In the final weeks of the mission, Cassini executed 22 orbits that carried it between the innermost ring and the planet's cloud tops, a region never previously explored. These final passes allowed direct measurements of Saturn's gravitational field at unprecedented precision, providing data that will constrain models of the planet's interior structure for decades. On September 15, 2017, with its fuel reserves depleted and its mission formally concluded, Cassini was directed into Saturn's atmosphere. The decision to destroy the spacecraft rather than leave it drifting in the system was made to protect Enceladus and Titan from any possibility of contamination by terrestrial microorganisms. Cassini entered the atmosphere, its thrusters firing to keep it oriented for as long as possible, transmitting data to Earth until the signal was lost. The spacecraft that had spent 20 years in space and 13 years in orbit around Saturn ended its mission by becoming part of the planet it had studied. The gas and ice giants of our solar system are not peripheral features of a system organized primarily around the inner rocky planets. They are the dominant gravitational agents in the system, the bodies that, through their formation and subsequent orbital evolution, shaped the architecture of everything around them. Jupiter's gravitational influence scattered material from beyond the frost line into the inner solar system, contributing the water and organic molecules that made Earth habitable. Saturn's gravitational resonance with Jupiter stabilized both planets' orbits over billions of years, preventing the kind of dynamical instability that might have sent them migrating inward. Neptune's migration through the outer disk scattered the Kuiper belt into its current configuration, and may have sent a pulse of comets into the inner solar system in the event geologists call the Late Heavy Bombardment. The story of the gas giants is not in the end a story about planets. It is a story about how planetary systems work, how the physics of gas, dust, gravity, and time interact to produce structures stable enough to persist for billions of years. It is a story about the improbability of any given outcome, about how slightly different initial conditions produce radically different systems, and about how the system we find ourselves in, with its two gas giants safely in the outer reaches, its rocky inner planets, its asteroid belt and Kuiper belt and distant Oort cloud, may be not quite typical and maybe not quite coincidental. Every observation we make of Jupiter's interior, every measurement of Neptune's wind speeds, every sample collected from the plumes of Enceladus adds a piece to a picture we are still assembling. The gas giants were the largest things to form around our Sun. They are the oldest witnesses to the conditions that prevailed when the solar system was young. And they are still, despite decades of dedicated study, mostly unknown engines of physics operating at scales and in regimes that our instruments can only partially reach and our models can only approximately describe. We have sent 6 spacecraft to the outer solar system. We have achieved one flyby of Uranus and one of Neptune, both by Voyager 2 in the 1980s. There are no approved missions currently en route to either ice giant. The gas giants are our nearest neighbors in the class of objects that dominate the universe's planetary population, and we have barely touched them. What remains to be discovered about these worlds is almost certainly more than what has already been found. The detection of gas giants around other stars has transformed them from objects of local interest into probes of universal processes. The transit method, which detects the slight dimming of a star's light as a planet passes across its face, is most sensitive to large planets on short orbits. Hot Jupiters, the class of gas giants found orbiting very close to their host stars, are therefore overrepresented in the exoplanet catalog relative to their actual abundance. They make up only a small fraction of planetary systems when estimated through statistical correction. Perhaps 1 to 2% of Sun-like stars host one. But they were discovered first, studied most extensively, and they continue to challenge our models of planetary formation and migration in ways that have not been fully resolved. What makes hot Jupiters particularly puzzling is not just their existence close to their stars, but the absence of other planets around them. In our solar system, the region interior to Jupiter is populated by 4 rocky planets. Systems hosting hot Jupiters tend to have no such companions. The most likely explanation is that the inward migration of a gas giant, a process requiring interactions with the gas disk or with other planets through gravitational scattering or through tidal forces from the star, is destructive to whatever else was forming in the inner system. A migrating Jupiter mass object sweeps up or ejects smaller bodies and disrupts the dynamical conditions necessary for rocky planet formation. Systems with hot Jupiters may simply have had their inner systems cleared in the process. Our own solar system appears to have avoided this fate, though perhaps not by much. Geochemical evidence from asteroid samples and from the compositional pattern of the asteroid belt suggests that Jupiter did migrate, but only modestly, inward and then outward again, in a pattern described by the Grand Teck hypothesis. In this model, Jupiter formed beyond the current snowline, migrated inward to approximately 1.5 astronomical units, roughly the current orbital distance of Mars before Saturn, growing and approaching Jupiter from the outer disk, became locked in a gravitational resonance with it. This resonance reversed Jupiter's migration and carried both planets outward to their current positions. Had Jupiter continued migrating inward without reversing, it might have passed through the region where Earth would later form, and the inner solar system might have been left with no rocky planets at all, or with a very different configuration than the one we inhabit. Uranus sits alongside Neptune as the second ice giant, and its scientific importance has been chronically underestimated. From a distance, Uranus appears featureless, a pale blue-green sphere without the bending of Jupiter or Saturn, without the visible storms of Neptune, apparently inert. This appearance is deceptive. Uranus is the coldest planetary atmosphere in the solar system, with a minimum temperature of -224 degrees Celsius, colder even than Neptune despite being approximately half as far from the Sun. The reason is thought to be related to Uranus's peculiar axial tilt of 98 degrees. It rotates essentially on its side, with its rotational axis nearly in the plane of its orbit. This means that its poles point almost directly toward the Sun during parts of its orbit, receiving prolonged continuous sunlight for decades at a time, and then plunging into prolonged darkness. The mechanism by which this geometry suppresses Uranus's internal heat output, if it does, is not understood. Unlike every other giant planet, Uranus emits almost no excess heat. It radiates approximately what it receives from the Sun. Whether this reflects a genuinely cold interior, an interior where heat is trapped by a compositional or thermal layer and cannot escape, or something else entirely, is an open question. Uranus's axial tilt was almost certainly produced by a collision, one or more giant impacts early in the solar system's history that knocked the planet onto its side. Such an impact would have been a collision with an object of at least Earth's mass occurring at a time when the protoplanetary disk was still dispersing and giant impacts between embryos and young planets were relatively common. The aftermath of this impact is encoded in Uranus's ring system, its unusual moon system, and the planet's internal structure, none of which have been studied from close range since Voyager 2's brief flyby in January 1986. The scientific case for a dedicated mission to the ice giants is one of the most compelling unsatisfied priorities in planetary science. At 1032's report from the National Academies of Sciences, Engineering and Medicine, the decadal survey that sets priorities for NASA planetary science, ranked an Uranus orbiter and probe as its top large mission priority for the coming decade. The case rests not only on the intrinsic scientific interest of Uranus and Neptune, but on the fact that ice giants appear to be the most common type of planet in the galaxy. Statistical analysis of exoplanet data suggest that planets in the size and mass range of Uranus and Neptune are more abundant than either terrestrial planets or gas giants. If this is correct, then the ice giants of our solar system are our nearest representatives of the most common planetary architecture in the universe, and we have almost no direct data about their interiors, their magnetic field generation, or their atmospheric dynamics at depth. Ganymede, the largest moon of Jupiter and the largest moon in the solar system, deserves attention beyond its record-setting size. It is larger than Mercury, though less massive due to its substantial water ice content. What makes Ganymede exceptional among moons is that it has its own magnetic field, the only moon in the solar system known to do so. The field creates a miniature magnetosphere embedded within Jupiter's vast one, forming auroral bands near Ganymede's poles that have been observed from Earth by the Hubble Space Telescope. The magnetic field requires an active dynamo, which in turn requires a conducting liquid layer in the interior, most likely an iron or iron sulfide core. Ganymede also likely hosts a subsurface ocean between layers of ice, sandwiched between an upper water ice crust and a lower ice phase that exists under the extreme pressures of the deep interior. The total water content of Ganymede's ocean may be several times larger than Earth's combined ocean volume. ESA's JUICE mission, Jupiter Icy Moons Explorer, launched in 2023 and will arrive at Jupiter in 2031, with Ganymede as its primary long-term target, eventually entering orbit around the Moon to study it in detail. Callisto, the outermost of Jupiter's 4 large Galilean moons, occupies a strange position in the hierarchy of solar system objects. It is almost as large as Ganymede, nearly 5,000 kilometers in diameter, but its interior appears to be largely undifferentiated. Where Ganymede has an iron core, a rocky mantle, and an icy shell, Callisto appears to be a roughly uniform mixture of rock and ice throughout, as if it never underwent the heating necessary to separate its components. Callisto is covered in ancient impact craters, among the highest density of craters of any object in the solar system, indicating a surface that has remained geologically inactive since the early period of heavy bombardment billions of years ago. Why Callisto differs so dramatically from the similarly sized Ganymede, despite the two moons forming from the same circumplanetary disk around Jupiter, is not known. The difference in their geological histories may reflect differences in their formation timescales or in their early orbital evolution questions that the JUICE mission's observations may help answer. The question of moons around gas giants extends far beyond our solar system in implication, even though we have not yet confirmed the detection of a moon around any exoplanet. The search for exomoons is technically demanding. The signature of a moon is a small perturbation on top of the already small perturbation of the planet itself, but it is scientifically motivated by exactly the case of Europa and Enceladus. If gas giants in other systems carry with them the same diversity of icy moons, and if tidal heating operates similarly, then habitable environments may be far more common than surface-level assessments of the habitable zone would suggest. A gas giant orbiting at the inner edge of the habitable zone might itself be uninhabitable, but its moons might be ideal. A gas giant orbiting outside the habitable zone, kept warm by tidal forces, might host moons with liquid water oceans in perpetual darkness, sustained by internal heat rather than starlight. The gas giant becomes not an obstacle to life, but a source of the energy that makes it possible. Saturn's ring system provides a compressed laboratory for studying the processes that shape the entire solar system. The dynamics of the rings, the way particles interact gravitationally, collide inelastically, form wakes and density waves and gaps, respond to the gravitational resonances of moons, are governed by the same physics that governed the protoplanetary disk from which all the planets form. Studying the rings gives planetary scientists a tool for testing models of disk physics in real time. In a system, we can observe at high resolution, rather than relying entirely on numerical simulations of processes that occurred 4.5 billion years ago and left only indirect traces. The rings of Saturn are, in a sense, a planet formation disk frozen in miniature, playing out its dynamics at a scale and in a time frame accessible to human observation. The moonlets embedded within the rings, objects tens to hundreds of meters in diameter that were revealed by the Cassini mission, behave exactly as planetary embryos are predicted to behave in a protoplanetary disk. They gravitationally focus material from their surroundings, creating propeller-shaped disturbances in the ring texture that can be tracked as they orbit. Some of these moonlets drift in their orbital positions over time, driven by gravitational interactions with the surrounding ring particles, a behavior analogous to the orbital migration of young planets interacting with a gas disk. The rings are not just aesthetically striking, they are a working model of planetary system formation. Looking outward across the solar system from the vantage point of Earth, the four gas and ice giants, Jupiter, Saturn, Uranus, Neptune, form a kind of gravitational shell around the inner system. They are the gatekeepers of the Kuiper belt and the Oort cloud, the sources of the long-period comets that occasionally enter the inner system carrying pristine material from the solar system's formation. They are the bodies that deflected, scattered, and sometimes captured the material that populates the asteroid belt and the Trojan clouds at Jupiter's Lagrange points. They are the reason the inner solar system is as dynamically stable as it is, and they are also the reason it was as violently bombarded as it was in its first billion years. Every time a gas giant forms, it rewrites the history of every other body in its system. Every time one migrates, it sends ripples through the architecture of everything around it. The giant planets are not just planets. They are events, prolonged, ongoing events, whose consequences are still playing out, still being felt by the smaller bodies that orbit in their shadow, still being recorded in the geological histories of worlds like Earth, Mars, and the asteroids. To understand the solar system is, in large part, to understand the gas giants. And to understand the gas giants is to understand ourselves, where we orbit, why our world is the way it is, and how contingent the whole arrangement truly is. We did not have to be here. The conditions that produced a solar system with Jupiter in a stable outer orbit, Saturn locked in resonance with it, two ice giants beyond, and four rocky planets inside, those conditions were not predetermined. They were the outcome of a chaotic process that could have gone differently at many points, and did go differently in most other systems we have observed. The gas giants of our solar system are not the backdrop against which Earth's story plays out. They are, in a very real sense, part of the reason there is a story to tell at all. The relationship between a star's chemical composition and the likelihood of hosting gas giants is one of the more statistically robust results to emerge from exoplanet surveys. Stars with higher concentrations of elements heavier than helium, a property astronomers call metallicity, are significantly more likely to host gas giants than metal-poor stars. The correlation is strong enough that metallicity is now used as a predictor of gas giant likelihood when assessing newly discovered planetary systems. The interpretation is straightforward. Metal-rich stars formed from denser, more chemically complex protoplanetary disks. Those disks contained more solid material, enabling cores to grow more rapidly and reach the runaway accretion threshold before the gas disk dispersed. Stars with low metallicity, like many of the ancient population 2I stars in the galactic halo, may almost never host gas giants formed through core accretion. Their disks were thin, their solids sparse, and the window for core assembly closed before any embryo grew massive enough to trigger gas accretion. Our Sun sits near the metal-rich end of the distribution for stars of its age. It formed roughly 4.5 billion years ago in a molecular cloud that had been enriched by several generations of stellar nucleosynthesis, the deaths of earlier stars that scattered carbon, oxygen, silicon, and iron into the interstellar medium. This enrichment gave the protoplanetary disk enough solid material to build Jupiter and Saturn rapidly, before the solar wind dispersed the gas. Stars that formed earlier in the galaxy's history, when the interstellar medium was less chemically processed, had thinner, more hydrogen-dominated disks and are correspondingly less likely to have gas giants. When we search for planetary systems most likely to resemble our own, metallicity is one of the first filters applied. The boundary between a gas giant and a brown dwarf is not a line, but a transition, Brown dwarfs are substellar objects too massive to be gas giants in the conventional sense, but not massive enough to sustain the hydrogen fusion that powers a true star. The minimum mass for a hydrogen-burning star is roughly 80 Jupiter masses. Brown dwarfs occupy the range from approximately 13 to 80 Jupiter masses. Below 13 Jupiter masses, the approximate threshold for deuterium fusion, objects are classified as planets, or in some usage as superjupiters or massive gas giants. The 13 Jupiter mass boundary is itself somewhat arbitrary, defined by a nuclear process that has no direct bearing on formation mechanism or observable structure. This ambiguity matters because the formation mechanisms for massive gas giants and low-mass brown dwarfs may overlap. A very massive gas giant formed through core accretion looks from the outside, identical to a low-mass brown dwarf formed through gravitational instability. Their atmospheric compositions, their temperatures, their emission spectra are similar. Only their formation histories differ, and those histories are inaccessible to observation. In some cases, objects in the 10 to 15 Jupiter mass range are classified differently by different researchers, depending on whether they emphasize formation mechanism or mass as the defining criterion. The boundary between planet and star at the extremes of the mass function is genuinely uncertain. Jupiter at 318 Earth masses is well below this ambiguity zone, but its growth may have been limited more by the availability of gas in its feeding zone than by any intrinsic ceiling. Had Jupiter formed in a more massive or more extended disk, it might have continued accreting and reached brown dwarf mass. What we call Jupiter is, in one sense, a gas giant that simply ran out of food before it grew large enough to change categories. The solar system would look very different if Jupiter had reached 10 times its current mass. The inner planets might not exist in recognizable form, and the architecture of the outer system would be entirely unlike what we observe. The history of the outer solar system is partly encoded in the current distribution of small bodies beyond Neptune. The Kuiper belt, a disk of icy objects extending from Neptune's orbit at 30 astronomical units to roughly 50 astronomical units, contains hundreds of thousands of objects larger than 100 kilometers in diameter and billions of smaller ones. Its structure is not smooth. It has gaps and concentrations, resonance populations locked in precise orbital ratios with Neptune, and a sharp outer edge at around 48 astronomical units that was not predicted by early solar system models. These features are the fingerprints of Neptune's outward migration through the outer solar system early in its history. The most widely accepted model for this migration is the Nice model, named for the French city where it was developed in the early 2000s. In this framework, the four giant planets originally formed in a more compact configuration, all within 20 astronomical units of the Sun, with Jupiter and Saturn just inside a 1-to-2 orbital resonance, a configuration in which Jupiter completed exactly 2 orbits for every one of Saturn's. The interaction between the giant planets and the dense disk of planetesimals beyond them was initially in approximate equilibrium, with the giants exchanging angular momentum with the disk but not migrating dramatically. When Jupiter and Saturn drifted into the exact 1-to-2 resonance, however, the dynamics changed abruptly. Their gravitational interaction intensified, and the system entered a phase of instability that sent Uranus and Neptune on outward migrating trajectories through the planetesimal disk. As Neptune plowed outward, it scattered the planetesimal disk in all directions. Some objects were flung inward into the inner solar system, producing a pulse of bombardment the geologists call the Late Heavy Bombardment, a period approximately 3.9 billion years ago, when the rate of asteroid and comet impacts on the Moon and inner planets increased dramatically before subsiding. Evidence for this event is preserved in the impact record of the lunar highlands. Other objects were pushed into stable resonances with Neptune rather than being scattered, forming the resonant Kuiper belt populations we observe today. Objects in the 2-3 resonance with Neptune completing 2 orbits for every 3 of Neptunes are called Plutinos, the largest of which is Pluto. Objects at other resonances form similarly distinct populations. The structure of the Kuiper belt is an archive of planetary migration, a record in ice and rock of where Neptune was and how it moved. The Trojans of Jupiter, populations of asteroids locked in Jupiter's 1Q1 resonance, occupying stable gravitational equilibrium points 60 degrees ahead of and behind Jupiter in its orbit, tell a related story. The Trojan populations are unexpectedly large and unexpected in their composition. Many Trojans appear dark and reddish, with spectral properties suggesting organic-rich surfaces similar to those of Kuiper belt objects rather than the dry silicate material of the main asteroid belt. This is consistent with the NICE model's prediction that outer solar system material was scattered widely during the instability period, with some of it being captured into Jupiter's resonance rather than being expelled from the system or delivered to the inner planets. The Trojans are, in this interpretation, captured members of the primordial outer disk, visitors from beyond Neptune's current orbit that were trapped near Jupiter when the planets were still migrating. NASA's Lucy mission, launched in 2021, is currently on an extended tour of Jupiter's Trojan asteroids. It will fly past 6 Trojans between 2027 and 2033, making close-range observations of these ancient objects for the first time. Because the Trojans are believed to preserve the composition of the outer solar system before planetary migration disturbed it. They may carry information about the solar system's initial chemical inventory in a way that material from the inner system, which has been processed by solar heating and hydrothermal chemistry, does not. Lucy will also fly past a main belt asteroid on its way, providing compositional context for comparison. The Juno spacecraft, which entered orbit around Jupiter in July 2016, has provided more data about Jupiter's interior and atmosphere than any previous mission. Its instruments measure Jupiter's gravitational and magnetic fields at unprecedented precision, and its orbit, a highly elliptical polar orbit that carries it within 5,000 kilometers of the cloud tops at each closest approach, takes it through regions of the Jovian magnetosphere that had never been directly sampled. What Juno has found challenges several long-standing assumptions. The gravitational field measurements reveal that Jupiter's interior is not layered in the simple way models predicted. The heavy elements oxygen, carbon, nitrogen, sulfur, and heavier species are not cleanly separated into a compact core with a pure hydrogen-helium envelope above it. Instead, they appear to be distributed throughout a large fraction of the planet's radius, with their concentration gradually increasing toward the center, rather than jumping sharply at a core boundary. This dilute core, as it has been called, extends to roughly half of Jupiter's radius, a volume that would contain dozens of Earths. The most likely explanation is that an early giant impact disrupted a more compact original core, mixing its material outward into the envelope. If so, Jupiter carries within it a record of one of the most violent events in the solar system's history, an impact so large it restructured the interior of the largest planet. Juno's microwave radiometer has also probed Jupiter's atmosphere to depths far below anything previously achievable. The instrument measures thermal emission at wavelengths between 1 and 50 centimeters, which penetrate the atmosphere to pressures of hundreds of atmospheres, far deeper than any optical or near-infrared observation. What it has found is that Jupiter's atmosphere is not uniform at depth. The ammonia distribution in particular is highly non-uniform, rather than being well mixed at pressures below the ammonia cloud base. Ammonia shows dramatic latitude-dependent variations extending hundreds of kilometers into the planet. There are regions of high ammonia concentration and regions depleted of ammonia, organized in patterns that mirror the banding visible at the surface but extending far deeper than models predicted. The mechanism that maintains this structure, likely a combination of large-scale circulation and phase changes of ammonia in the deep atmosphere, is not yet understood. The auroras of Jupiter, observed by Juno in detail for the first time from close range, are more complex and more energetic than any previous measurement suggested. They are powered by multiple mechanisms simultaneously. The interaction of the solar wind with the magnetosphere, the co-rotation breakdown of Io's plasma torus, the coupling of magnetic field lines to the rapidly rotating planet, and the precipitation of energetic particles along field lines connected to Io, Europa, and Ganymede. Each moon leaves its own auroral footprint in Jupiter's polar atmosphere, a series of glowing spots that trace the magnetic connection between the moon's orbit and the atmospheric layer, where energetic electrons deposit their energy. The Io footprint, brightest of the three, can be tracked as it moves across the auroral oval, with Io's orbital period of 1.77 days. Jupiter's aurora is not a passive response to the solar wind. It is an actively driven process, powered largely by the planet's own rotation and its interaction with the volcanically supplied plasma from Io. Saturn experienced one of its most dramatic observable events in December 2010, when a powerful convective storm erupted in the northern hemisphere and rapidly encircled the entire planet. Called the Great White Spot, a feature that has appeared roughly once per Saturnian year, or every 30 Earth years since records began. The 2010 storm was the largest and most energetically intense on record. Within a few weeks, the storm head had expanded into a band of bright cloud spanning more than 15,000 kilometers, and the disturbance it generated propagated eastward around the planet at hundreds of kilometers per hour. By the time it had circled the globe and re-encountered the original storm head, the interaction produced a particularly violent atmospheric event visible in both visible and radio wavelengths. The Cassini spacecraft, already in orbit, observed the entire development from nearby, tracking lightning discharges within the storm that were detectable as radio emissions from millions of kilometers away. At its peak, the lightning flash rate within the storm exceeded 10 strikes per second, an intensity more than 10,000 times greater than typical terrestrial thunderstorm activity. The energy source for this storm was the latent heat stored in Saturn's deep atmosphere. Saturn's periodic great white spots are thought to be triggered when a convective plume breaks through a stable layer in the upper troposphere, releasing stored thermal energy explosively. The 30-year periodicity corresponds to the time required for the energy to accumulate in the lower atmosphere between events. Saturn is not a placid world. The calm appearance of its bands relative to Jupiter's turbulent face is misleading. The energy is there, stored below the visible cloud tops, released periodically in events of planetary scale. Jupiter is not the only giant planet with a ring system. All 4 outer planets in our solar system have rings, a fact that was not known until the 1970s. Jupiter's rings were first detected by the Voyager 1 spacecraft in 1979, 3 years after the rings of Uranus were discovered through stellar occultation measurements from Earth, when Uranus passed in front of a star and its rings briefly blocked the starlight before and after the planetary disk occulted it. Neptune's rings were confirmed by Voyager 2 in 1989. Jupiter's ring system is thin, faint, and composed primarily of dust rather than ice. Unlike Saturn's rings, which are bright because they are made of highly reflective water ice, Jupiter's rings are dark, visible only in scattered light when viewed at specific geometries. They are composed of silicate dust blasted off the small inner moons Metis, Adrastea, Amalthea, and Thebe by micrometeorite impacts. This dust is continuously lost from the ring, swept inward by electromagnetic forces and orbital decay, and continuously replenished by new impacts on the moons. Jupiter's ring system is not a stable, long-lived structure, but a continuously renewed stream of ejecta, maintained in a dynamic equilibrium between loss and replenishment. The rings exist because the moons are there. If the moons were removed, the rings would disappear within a geologically brief interval. Uranus has a ring system of intermediate character, darker than Saturn's but more structured than Jupiter's. Its rings are narrow, confined by small shepherd moons that gravitationally constrain the ring particles to well-defined radial bands. The rings of Uranus are composed of dark, macroscopic particles, objects centimeters to meters in size, unlike the micrometer scale dust of Jupiter's rings. Their dark color, like that of Jupiter's ring particles, likely reflects a coating of complex organic material produced by radiation processing of icy surfaces. Uranus's rings are also young by planetary standards, probably no more than a few 100 million years old, formed from the disruption of a small moon or captured object rather than being primordial. The Hubble Space Telescope and Keck Observatory have tracked changes in Uranus's ring system over decades, observing shifts in ring geometry and the brightening of the outer epsilon ring, which is the most massive and most well-defined of the system. The moons of Uranus are smaller and less studied than those of Jupiter or Saturn, but several are geologically interesting in ways that a single Voyager flyby could only hint at. Miranda, the innermost of the 5 large moons, has a surface unlike any other in the solar system. It appears to be a patchwork of radically different terrain types, ancient cratered plains, chaotically fractured regions called coronae, and enormous cliff faces, including Verona Rupes, a scarp roughly 20 kilometers high, that is the tallest known cliff in the solar system relative to the body's own gravity. Several explanations have been proposed for Miranda's bizarre surface. The original hypothesis was that Miranda had been shattered by an impact and reassembled in a chaotic configuration. More recent work suggests the coronae may be the result of partial melting and convective upwelling of ice, internally driven tectonics on a body barely 500 kilometers in diameter. Miranda may be geologically active in ways that its small size and remote location would not suggest. The atmospheric composition of gas giants in other solar systems has become directly measurable through the application of transmission spectroscopy, a technique in which the spectrum of a star is measured during a planetary transit and compared with a spectrum measured outside transit. The difference encodes the absorption signature of the planetary atmosphere, which the starlight passes through as it grazes the planet's limb on its way to the telescope. This technique works best for large planets on close orbits, conditions that make hot Jupiters the most accessible targets. But it has now been applied to dozens of exoplanet atmospheres. The James Webb Space Telescope, launched in December 2021, has transformed this field. Its sensitivity in the infrared, combined with its location at the second Lagrange point beyond Earth's orbit, free from the blurring effects of Earth's atmosphere, allows it to detect atmospheric constituents in exoplanet spectra at a level of precision far beyond what previous facilities could achieve. Its first year of science observations included detailed spectroscopic measurements of the hot Jupiter WASP-39b, a planet roughly the mass of Saturn orbiting a sun-like star in the constellation Virgo at a distance so close that its year lasts just over 4 Earth days. The Webb spectrum of WASP-39b detected carbon dioxide, water vapor, sodium, potassium, sulfur dioxide, and carbon monoxide in the planet's atmosphere. The sulfur dioxide detection was particularly significant. It is produced by photochemical reactions driven by the intense ultraviolet radiation from the star, and its detection represents the first direct evidence of photochemistry in an exoplanet atmosphere. The same processes that produce complex organic molecules in the atmospheres of Titan and Jupiter are operating in the atmosphere of a planet 47 light-years away, and we can now detect them. Webb has also observed directly imaged gas giants, young, massive planets that orbit their stars at large separations and are bright enough in the infrared to be detected separately from their host star's light. The thermal emission from these planets, still warm from the energy of their formation, encodes their composition and atmospheric structure in their infrared spectra. These direct emission measurements complement the transmission spectra of transiting planets, which are biased toward the day-night terminator region. By probing the day-side atmospheric structure where thermal emission is strongest. Together, the two techniques are beginning to build a comparative picture of gas giant atmospheres across a range of masses, temperatures, and orbital configurations. A comparative planetology of gas giants that extends from Jupiter and Saturn to hundreds of worlds in other star systems. What this expanded survey is revealing is that gas giant atmospheres are highly diverse, in ways that our 4 local examples only begin to sample. Some hot Jupiters have thermal inversions, regions where temperature increases with altitude rather than decreasing, as it does in Jupiter's troposphere produced by the absorption of intense stellar radiation by high-altitude absorbers, possibly titanium oxide or vanadium oxide. Others show signs of silicate clouds at high altitudes, where the extreme temperatures keep minerals vaporized in the lower atmosphere, but allow them to condense into cloud particles higher up. Some have detectable wind patterns, asymmetries between the dawn limb and the dusk limb of the planet that reflect the atmospheric circulation patterns driven by the enormous temperature. Contrast between the permanently day-side and permanently night-side hemispheres of tidally locked hot Jupiters. None of these phenomena exist in our solar system's gas giants, because our gas giants orbit far enough from the Sun that tidal locking never occurred, and the day-night temperature contrast is minimal. Hot Jupiters are not exotic aberrations of planetary science. They are end-member cases in the parameter space of gas giant conditions, and studying them illuminates the physics of gas giant atmospheres, in the same way that studying Venus and Mars illuminates the physics of terrestrial atmospheres. The magnetic fields of the 4 outer planets span nearly 2 orders of magnitude in surface field strength and exhibit geometries that range from nearly perfectly aligned with the rotation axis in Saturn's case to dramatically offset and tilted in Uranus and Neptune's case. Understanding why these differences exist is one of the major unsolved problems in planetary magnetism. The generation of a planetary magnetic field through dynamo action requires a conducting fluid, differential rotation, and convection. All 4 giants satisfy these conditions, but the specific geometry of the field depends on the radial structure of the conducting region, the nature and location of the convective flows, and the interaction between the field and the rotation. In Earth's case, the field is generated in the liquid iron outer core, a relatively thin shell around a solid inner core. In Jupiter and Saturn, the field is generated in the metallic hydrogen envelope. In Uranus and Neptune, it appears to be generated in the conducting icy mantle, a compositionally very different material at very different conditions. The peculiarity of Saturn's magnetic field is that it is within measurement precision perfectly symmetric with respect to the planet's rotation axis. This is unexpected. Theoretical work on dynamo generation predicts that a purely axisymmetric field should be unstable, unable to sustain itself against the dissipative forces that erode it. Saturn's field appears to violate this prediction. One proposed resolution is that the outer layers of Saturn's atmosphere below the visible cloud tops are differentially rotating at rates different from the deep interior, and this differential rotation creates a shearing flow that forces the magnetic field into axisymmetry even against its natural tendency to develop tilt and offset. The Cassini mission made the most precise measurements of Saturn's magnetic field ever obtained. And even those measurements could not detect a departure from axisymmetry at the level of 1/10 of a degree. Whatever mechanism maintains this symmetry is unusually effective. the question of what future missions will reveal about the gas and ice giants is not merely academic. The Uranus orbiter recommended by the 2022 Planetary Science Decadal Survey would be the first dedicated mission to either ice giant and would carry a probe designed to enter Uranus's atmosphere directly, measuring composition, temperature, and wind speed at depths inaccessible to remote sensing. The scientific return from such a mission would be comparable to the return from Galileo's atmospheric probe at Jupiter in 1995, which revealed that Jupiter's atmosphere was drier, had stronger winds, and had a different elemental composition than pre-mission models predicted, forcing a revision of planetary formation models that was still being processed decades later. A probe into Uranus's atmosphere would almost certainly produce similar surprises, because our current knowledge of Uranus's interior and atmospheric structure is based largely on the data collected during 45 minutes of Voyager 2's closest approach in January 1986. 45 minutes of data from one flyby is not a foundation for confident models. A mission to Neptune faces greater challenges. The travel time to Neptune's distance from Earth is roughly 12 years, even on an optimized trajectory. And the power supply for a spacecraft operating that far from the Sun requires either advanced solar arrays or radioisotope thermoelectric generators at a scale not currently in production. Both obstacles are surmountable, but they make a Neptune orbiter a longer-term prospect than the Uranus mission. The scientific case, however, is compelling. Triton's captured orbit, its active geysers, and its inevitable tidal dissolution make it a scientifically unique object. The possibility that Triton harbors a subsurface ocean heated by the residual energy of its orbital circularization has been raised seriously in the literature. If Triton has liquid water beneath its surface, and if organic chemistry has been operating there since its capture, it represents another candidate for life at the outer edge of the solar system, in a body that did not originate around the Sun at all. Titan is the target of NASA's Dragonfly mission, a rotorcraft lander scheduled to launch in 2028 and arrive at Titan in 2034. Dragonfly will not orbit Titan, but will fly through its atmosphere, landing at multiple sites separated by tens of kilometers and conducting chemical analysis of the surface and shallow subsurface at each. It will visit the Selk impact crater, a relatively young impact structure where the heat of the impact would have transiently melted Titan's water ice crust, creating a brief warm wet environment where water and the organic molecules abundant in Titan's surface material could have interacted in ways potentially relevant to prebiotic chemistry. On Earth, the chemistry of life's origin is thought to have required liquid water in contact with organic molecules and some source of chemical energy. Selk crater may have provided all three for a period of perhaps thousands of years following the impact. Whether any interesting chemistry actually occurred and whether Dragonfly's instruments can detect the products is unknown, but it is a question that can now be asked with hardware rather than inference. The relationship between gas giants and the origin of life on Earth is indirect but not negligible. The delivery of water to Earth is a problem that planetary scientists have not fully solved. The Earth formed in a region of the solar system where water should have been largely absent, interior to the frost line, where water ice could not condense from the solar nebula. The water on Earth's surface must have been delivered after the planet formed, most likely by objects from the outer solar system that were scattered inward by gravitational interactions. Jupiter is the primary gravitational scattering agent in the outer solar system. It is Jupiter that deflects comets from the Kuiper belt and Oort cloud onto orbits that bring them into the inner system. It is Jupiter's gravitational resonances that drive asteroids from the outer main belt, the C-type carbonaceous asteroids that contain water in hydrated minerals and organic material in abundance, into Earth-crossing orbits. Without Jupiter, the delivery of water and organics to the early Earth would have been far less efficient. The same mechanism that delivers life-essential material to Earth also, at times, delivers catastrophic impactors. Jupiter's gravity can steer large objects into Earth-crossing orbits as well as small ones. The Chicxulub impactor that ended the reign of the non-avian dinosaurs 66 million years ago was a body roughly 12 kilometers in diameter. Its origin in the outer solar system is suspected but not confirmed. Jupiter's influence on the rate of large impacts in the inner solar system over geological time is a genuine scientific question, with some models suggesting it has on net protected Earth from a higher rate of large bombardments by deflecting potential impactors out of the inner system, and other models suggesting it has, at times in the solar system's history, increased bombardment rates by scattering material inward. The net effect of Jupiter's presence on the long-term habitability of Earth is still being debated. What is not debated is that planetary systems with gas giants in outer orbits are less common than planetary systems without them. Statistical analyses of the Kepler mission's planet catalog, corrected for observational biases, suggest that solar system analogues with outer gas giants and inner rocky planets may represent only a few % of planetary systems around Sun-like stars. Most planetary systems found to date have their largest planets either very close to the star, in highly eccentric orbits, or not present at all. The solar system's architecture, with its 2 stable outer gas giants, its 2 moderate ice giants beyond them, and its 4 small rocky planets in the inner system, appears to be relatively unusual. This does not mean it is unique, with hundreds of billions of stars in the galaxy. Even a few % frequency implies billions of solar system analogues. But it does mean we should not assume that our planetary system is a typical outcome of the planet formation process. Every gas giant we study, whether it orbits our own sun or a star 40 light-years away, adds to our understanding of this process. Every measurement of Jupiter's gravitational harmonics by Juno, every spectroscopic detection in the atmosphere of a hot Jupiter by Webb, every image of a storm system in Saturn's northern hemisphere by Cassini's legacy dataset, each one is a piece of a large and still mostly incomplete picture. The physics governing these objects operates on scales from quantum mechanical electron behavior in metallic hydrogen to the gravitational interactions of planets spread across billions of kilometers. No single observation resolves all the questions. The questions are in many cases so large and so deeply embedded in the fundamental physics of matter at extreme conditions that answering them may take generations. But the inquiry is not merely academic. To understand gas giants is to understand how planetary systems are built, how they evolve, how they influence the smaller worlds that orbit alongside them, and ultimately how worlds like Earth, with their liquid water, their complex chemistry, their capacity for life, come to exist at all. The gas giants are not incidental to that story. They are structural elements of it, written in hydrogen and helium and ice, broadcasting their presence through gravitational fields that reach across the solar system and influence every orbit within it. They formed first, they reorganized everything that came after, and they are still 4.5 billion years later, the dominant dynamical forces in the system they inhabit. In any accounting of what our solar system is and why it looks the way it does, the gas giants come before everything else. There is a subtler dimension to gas giant science that receives less attention than interior structure or atmospheric chemistry, but that may ultimately prove as important: the question of how gas giants interact with one another over the lifetime of a planetary system. Our solar system's 4 outer planets are, at present, dynamically stable. Their orbits oscillate within bounded ranges. Their gravitational interactions average out over long time scales, and the system will remain in approximately its current configuration for billions of years into the future. this stability was not guaranteed in the early solar system during the instability phase described by the NICE model. The outer planets' orbits were chaotic in the technical sense. Small differences in initial conditions produced very different outcomes. The solar system that emerged from that instability is one of the stable configurations that the chaos allowed, but it is not the only one that was possible, and it is not the configuration with the highest probability. Most runs of NICE model simulations that begin with the observed initial conditions of the outer solar system produce architectures that differ significantly from the one we observe with the fifth giant planet ejected, or with Neptune and Uranus exchanging positions, or with Saturn scattered outward to a much larger orbit. The NICE model, as originally formulated, required the starting configuration to include a fifth giant planet, an ice giant of roughly Neptune's mass, to drive the instability while preserving the remaining 4 planets. This hypothetical fifth giant would have been ejected during the instability phase. Its orbital energy exchanged with one of the remaining planets before it was flung into interstellar space on a hyperbolic trajectory. Simulations show that such an ejected planet could exist today, traveling through the interstellar medium at a velocity comparable to other free-floating planetary mass objects, rogue planets, that have been detected through gravitational microlensing surveys. Whether the solar system's fifth giant, if it existed, has ever been observationally detected is unknown. There are billions of rogue planets in the galaxy, produced by the dynamical instabilities of planetary systems across the Milky Way's history, and identifying one as specifically originating from our own solar system would require determining its velocity vector and tracing it back to the Sun, a measurement far beyond current capabilities. The ejection of planets from forming systems is a common outcome of the planetary formation process across the galaxy. Gravitational microlensing surveys, which detected the temporary brightening of background stars as a massive object passes close to the line of sight and gravitationally focuses the background light, have detected a population of free-floating planetary mass objects that is large enough to suggest that ejected planets outnumber bound planets in the galaxy. The ejection process is most efficient during the early chaotic phases of planetary system evolution, when planets are still interacting strongly with one another and with the remnants of the protoplanetary disk. A gas giant that forms on a mildly eccentric orbit and then encounters another giant planet at close range can undergo a gravitational slingshot that removes it from the system entirely. The planet it ejected may then settle into a more circular orbit. The same dynamical exchange that sends one planet outward into interstellar space tends to send the remaining planet inward toward a more circular, stable orbit. Many of the hot Jupiters observed in close orbits around their stars may have arrived there through exactly this kind of gravitational scattering, rather than through the slower disk-driven migration that the original disk interaction models proposed. The distinction between these two migration mechanisms, disk migration and scattering, has observational signatures. Disk migration preserves the alignment between the planetary orbit and the stellar equatorial plane, because the disk from which the planet formed is itself aligned with the stellar equator by the physics of its formation. Scattering does not preserve this alignment. The final orbit of a scattered planet can be tilted at any angle relative to the stellar equator, including retrograde, orbiting in the direction opposite to the star's rotation. Measurements of the angle between a hot Jupiter's orbital plane and its host star's equatorial plane, an observable called the spin-orbit angle or the Rossiter-McLaughlin angle, after the astronomers who developed the measurement technique have revealed that approximately 30% of hot Jupiter's orbit in significantly misaligned configurations and some orbit fully retrograde. This is inconsistent with pure disk migration, which predicts alignment. It is consistent with scattering, which allows any alignment. The current understanding is that both mechanisms operate, with disk migration dominating for some systems and scattering for others, and that distinguishing between them on a system-by-system basis requires additional observational constraints. The long-term stability of a planetary system with gas giants is sensitive to the mass and orbital spacing of those giants in ways that generate both stable and unstable configurations over timescales of billions of years. Numerical simulations of our own solar system's long-term evolution show that it is not, in the strictest sense, completely stable over timescales longer than a few billion years. Mercury's orbit is chaotically influenced by resonant interactions with Jupiter and Venus, and on timescales of a few billion years, there is a small but non-zero probability. Recent estimates suggest approximately 1% that Mercury could be scattered into a high eccentricity orbit that subsequently leads to a collision with Venus, Earth, or the Sun. The event is unlikely within the Sun's remaining lifetime on the main sequence. But the fact that it is possible at all is a reminder that even the seemingly serene current configuration of our solar system contains the seeds of its own eventual disruption. In systems with more massive gas giants, or with gas giants more numerous or more closely spaced than Jupiter and Saturn, dynamical instabilities arise more readily and more rapidly. Population synthesis models of planetary system formation, which simulate large numbers of systems with varying initial conditions and track their evolution to the present day, find that systems with multiple gas giants in moderately close orbits commonly experience violent dynamical rearrangements within their first few 100 million years. These rearrangements typically result in one or more planets being ejected, and the remainder settling into configurations with larger orbital separations and higher eccentricities. The eccentric gas giant orbits commonly observed in exoplanet surveys may be the signatures of exactly these early violent events, the scars of planetary encounters encoded in orbital shape rather than in surface geology. The gas giants are, in this sense, not just the largest planets. They are the most historically eventful ones. The bodies whose formation and subsequent gravitational interactions shaped every other element of the systems they inhabit, including the conditions under which smaller, rockier planets could form and survive. Every rocky planet in the inner solar system orbits where it does because Jupiter and Saturn ended up where they did. Every asteroid in the main belt occupies its particular orbit because Jupiter's gravitational resonances cleared certain regions and concentrated material in others. Every comet that periodically brightens the inner solar system sky was deflected from the Kuiper belt or Oort cloud by the gravitational influence of Neptune or Jupiter. The smaller worlds of the solar system are, in their current configurations, the residue of the gas giants' formation and migration, shaped by forces too large to have generated them, but too large also to have left them unchanged. Looking across the known population of planetary systems, what stands out is not the diversity of gas giants themselves, but the diversity of contexts in which they occur. Hot Jupiters orbit alone, their inner systems swept clean. Warm Jupiters, gas giants at intermediate distances sometimes have companions and sometimes do not, in proportions that constrain the frequency of different migration mechanisms. Cold Jupiters at orbital distances comparable to Jupiter and Saturn tend to be found in systems with multiple smaller planets interior to them, a pattern consistent with the idea that gas giants at large orbital distances stabilize rather than disrupt the inner system. The presence of a cold Jupiter in a planetary system is actually a positive statistical predictor of the presence of inner super-Earths, smaller rocky planets in the habitable zone, rather than a negative one, as was initially assumed. The relationship between gas giant architecture and inner system structure is more nuanced than simple dichotomies between good and bad giant configurations allow. Continued observation of gas giants in our own solar system remains productive even after decades of focused study. Each new Juno Peri Jove. Each closest approach of the spacecraft to Jupiter's cloud tops adds to a dataset of gravitational, magnetic, and atmospheric measurements that is slowly resolving the ambiguities in Jupiter's interior structure. Each season that passes gives Earth-based and orbital telescopes a new temporal window on the long-term evolution of Saturn's ring system, which is changing on observable timescales as material is lost to the planet and to interplanetary space. Each improvement in near-infrared spectrograph sensitivity gives astronomers a better view of Uranus and Neptune's cloud structures, which are now known to vary with season and possibly with the solar cycle in ways not yet mechanistically explained. The picture that is emerging from close-range spacecraft observations, from Earth-based telescopes, from the growing catalogue of exoplanets, and from the increasingly sophisticated numerical simulations that link all these observations into coherent models, is of gas giants as dynamic, evolving, deeply complex objects embedded in a process of planetary system evolution that continues to the present day. They are not finished products. They are intermediate states in a long evolution whose timescale is comparable to the age of the universe and whose ultimate endpoint, for any given planetary system, is the death of the host star. When the Sun becomes a red giant in approximately 5 billion years, expanding to engulf the inner planets and dramatically altering the orbits of the outer ones, Jupiter and Saturn will survive. Their orbits will shift as the Sun loses mass, moving outward as the gravitational well they orbit becomes shallower. The planet that is today invisible from Earth's surface for much of the year, requiring a telescope to resolve its disk, will be the dominant feature of the sky for any entity capable of observing it from the surface of whatever the outer solar system becomes. Gas giants outlast the environments they helped create. They are the most durable component of a planetary system, formed from its most abundant material, sustained by its most fundamental physics. That durability is why they matter to us now. They are our closest representatives of a class of object that occurs throughout the galaxy, and they are accessible to the kinds of detailed study that no other technique, not even the most advanced spectroscopy of exoplanet atmospheres, can replicate. Every spacecraft we send to the outer solar system carries instruments built at the current frontier of engineering and returns data that defines the frontier of our understanding. The questions those spacecraft answer are replaced by new questions that require new spacecraft, and the process continues. This is not a failure of science. It is science working correctly. The successive replacement of larger ignorance with smaller ignorance, the gradual narrowing of the gap between what we think we know and what we actually know. The gas giants were here long before us, forming in the first few million years of the solar system's history, while the processes that would eventually produce Earth were only beginning. They will be here long after us, orbiting the remnant of our star through epochs of time beyond the reach of any human imagination. We observe them now in this narrow window of cosmic history where we have the instruments and the curiosity to study them, and what we learn in this window will define the foundation on which all future understanding of planetary systems, our own and others, will be built. That is not a small thing. It may, in the fullness of time, be one of the most consequential intellectual projects our civilization undertakes. There is one more aspect of gas giant science that deserves mention before any account of these worlds can claim to be reasonably complete. The question of what they sound like, not in the literal acoustic sense. Sound does not propagate through the vacuum of space. And the interiors of gas giants, where acoustic waves do travel, are inaccessible to any instrument we have yet deployed, but in the sense that gas giants, like the Sun and other stars, oscillate, they ring like bells, vibrating in normal modes of pressure and gravity driven by internal convection and by the perturbations of their moons. The study of these oscillations, called seismology when applied to Earth and helioseismology when applied to the Sun, offers a way to probe the interior structure of a planet through the patterns of its vibrations at the surface. Attempts to detect the normal mode oscillations of Jupiter began in the 1990s, using ground-based spectrographs to measure small Doppler shifts in the planet's reflected sunlight. Confirmed detections of Jovian oscillations were finally reported in the 2010s, and Juno's instruments have contributed further evidence for specific modes. The frequency spectrum of Jupiter's oscillations is sensitive to the density and composition profile of the interior, the same principle that allows seismologists to infer the layered structure of Earth's interior from earthquake waves without ever drilling to the core. As detection and analysis techniques improve, planetary seismology may eventually be able to independently constrain Jupiter's core mass and the depth of its metallic hydrogen transition zone, complementing the gravitational field measurements from Juno with a completely different class of observational evidence. Saturn's rings serve an analogous function: spiral density waves in the rings generated by gravitational resonances between ring particles, and Saturn's normal mode oscillations carry information about the oscillation frequencies of the planet itself. The Cassini mission's detailed imaging of these ring wave patterns allowed the first comprehensive mapping of Saturn's oscillation spectrum, a technique called chronoseismology. The results have been used to constrain Saturn's interior structure independently of gravity measurements, and they have revealed the presence of internal composition gradients that simple layered models do not predict. Rings as a seismograph. Ice particles orbiting a gas giant, their positions disturbed by the planet's own vibrations, transmitting information about the planet's deep interior to a spacecraft camera, thousands of kilometers above. The elegance of the technique is matched by the sophistication of the physics it exploits. The outer planets of our solar system have been studied for decades with increasingly capable tools, and the pace of discovery has not diminished. Each new instrument brings new questions into focus. Each new mission resolves old ambiguities and generates new ones. The gas giants of our solar system are not solved problems. They are archives, deep, complex, still largely unread archives of the conditions that prevailed when the solar system was young and of the physical processes that operate at the extremes of pressure, temperature, and composition. Reading those archives is the work of planetary science, conducted across generations, across national boundaries, across the full range of observational and theoretical tools that human knowledge has produced. The gas giants are patient. The archive is vast. And there is time, though perhaps not as much as we often assume, to read as much of it as we can.